Hello. In today's video, we're given a problem that deals with a cylindrical tank where we're told that there is a height of the tank, which we define as capital H, and then there's fluid in the tank at a height that is defined as lowercase h. We are given the cross-sectional area of the tank, which we define as AC, and we are told that there's a pressure outside of the tank and a pressure inside of the tank, and also that there is a hole, a small hole in the bottom of the tank which fluid is flowing out, and we have the cross-sectional area of that hole defined as AH. So what we want to do is create a model of the height of the fluid over time, and obviously with a hole in the bottom of the tank, over time the fluid height is going to decrease. And so we can assume that this is at a steady state for the reason that the hole in the bottom is so small that the acceleration can be assumed to be 0 because the flow rate is not too rapid. So because of steady state and because of the assumption that acceleration is equal to 0, we can use something called Bernoulli's equation. And so Bernoulli's equation is as follows. It's the pressure at position 2 minus the pressure at position 1 divided by the density plus the velocity at position 2 squared minus the velocity at position 1 squared divided by 2 plus the gravitational acceleration times the quantity of the height of position 2 minus the height of position 1 equals frictional heating. So in this problem, we are assuming that frictional heating is equal to 0. And so looking at this, there's a few terms that we don't know, but our end goal is to find the velocity at position 2. And the reason for this is we can use the velocity to find the flow rate. So we define all the other terms in this equation and do the mass balance in order to find that velocity and isolate that velocity. So first, let's start with the pressure at position 2. This is going to be the pressure outside of the tank, which is the atmosphere, so we're going to have that as 101,325. Now the pressure at position 1, to find this, we can use the ideal gas law, which is pressure times volume equals number of moles times gas constant R times temperature. And so first, what is the volume? Well, the volume is just the area times height. And so in this case, it's the cross-sectional area of the tank times the height of the tank minus the initial height of the fluid. What is the number of moles? Well, the number of moles is just going to be the pressure times the volume divided by the gas constant R times the temperature. And so the pressure, that's the initial pressure that we have, so that's going to be 101,325. The volume, again, is just cross-sectional area, or area times height, so we have that cross-sectional area. And then the height of the fluid is constantly changing, which makes sense because the fluid is constantly, the amount of fluid is constantly changing, which means the number of moles is constantly changing. So that's going to be the height of the tank minus the height of the fluid, not the initial height, just the height of the fluid divided by gas constant R times the temperature. So now we have these two defined. If we were to plug it back into our pressure equation, which would be pressure equals number of moles times gas constant R times temperature divided by volume, that would give us that pressure at position 1 is 101,325 times the cross-sectional area times the height of the tank minus the height of the fluid divided by gas constant R times temperature, that entire quantity times the gas constant R times temperature, divided by the volume, so that's going to be the cross-sectional area times the height minus the initial height of the fluid. So crossing out like terms, we can cross out the gas constant R's, the temperatures, the cross-sectional area. So that leaves us with the pressure of position 1 is equal to 101,325 times the height of the tank minus the height of the fluid, all over the height of the tank minus the initial height of the fluid. So that gives us our pressure. So we have our pressure at position 2, pressure at position 1. We are going to move on to the velocities. So the velocity at position 1, which would be in the tank up here, because the cross-sectional area is so wide, we're going to assume that the velocity at position 1 is very small. And on top of that, if you square a very small number, you're going to get a even smaller number. So what we're going to do is assume that the velocity of position 1 is equal to 0. And so that leaves us with the velocity of position 2 squared over 2. We want to keep the velocity of position 2 because that's what we're going to use to find the flow rate. So moving on to this last term, we have the gravitational acceleration times the height of position 2 minus the height of position 1. So to do this, we have to determine which way is negative and which way is positive. So we're going to say that going down is going to be positive. So that would give us a positive gravitational acceleration because the fluid height is going down. And we're going to define our 0. So we can either define 0 at where the fluid height is or at the bottom of the tank. The only issue with defining 0 at where the fluid height is that the fluid height is constantly changing. So that means your 0 is going to be constantly changing, which creates a few problems. So the easiest thing to do would just to define this bottom here as equal to 0. And so that's going to give us that the gravitational acceleration, positive, times the quantity of the height of position 2, which is 0, minus the height at position 1, which is just going to be the fluid height, which is also constantly changing. And so that's going to give us a negative gravitational acceleration times the height. And so now we have all of our terms. We can plug it into the equation. And so plugging in pressure 1 or pressure 2 is going to be 101,325 minus pressure 1, which is the quantity of 101,325 times the quantity of the height minus the height of the tank minus the height of the fluid, divided by the height of the tank minus the initial height of the fluid. And we're going to divide that by the density. And then we're going to add the velocity at position 2 squared over 2. Again, that 1 we're going to assume is 0, so we just get rid of that term. And it's a negative gravitational acceleration times height of the fluid, so it's going to be minus gravitational acceleration times height of the fluid. And we're assuming that frictional heating is equal to 0, so that's going to all be set equal to 0. So now we can begin to simplify. So we can distribute out this 101,325. So that's going to leave us with times the quantity of 1 minus the height of the tank minus the height of the fluid divided by the height of the tank minus the initial height of the fluid. And so what we can actually do is distribute out a negative 101,325 instead, so we can switch those terms so it looks a little cleaner. So it's going to be the height of the tank minus the height of the fluid divided by the quantity of the height of the tank minus the initial height of the fluid minus 1 over the density plus velocity position 2 squared divided by 2 minus gravitational acceleration times height equals 0. And so now we can isolate the velocity position 2. So if we were to bring everything over to the other side, so we have the velocity of position 2 squared. First, let's bring over the negative gravitational acceleration times the height of the fluid. Because it's negative on this side, when we bring it over, it's going to be positive. So we have gravitational acceleration times the height of the fluid, and then we bring over this term. Because it's a negative term, we could actually bring it over here and make it positive, which is why we distributed out the negative earlier. So that's going to be 101,325 times the quantity of the height of the tank minus the height of the fluid, divided by the height of the tank minus the initial height of the fluid, minus 1 divided by density, and that is all going to be multiplied by 2, because the 2 in the denominator over there. And so lastly, what we can do is, because it's squared over here, we can square the whole, or get the square root of the whole thing. And so rather than drawing a giant square root, we can just write to the 1/2. And so that's our isolated velocity at position 2. So what does this have to do with finding out the flow rate and being able to figure out the model of the change in fluid over time? Well, flow rate is just the area times the velocity. So in this case, we have the cross-sectional area of the hole, because that's what the fluid is coming out of, times the velocity at position 2, because that's the velocity of what is going out of the tank. And so the change in the height of the fluid is just going to be the change in the volume of the fluid over time, which that's going to be equal to the negative flow rate, because that's what's going out, that's what's causing the change in the fluid. And so that's just going to equal the negative cross-sectional area of the hole times the velocity at position 2, which is this equation that we derived here. And so change in volume over change in time, well, the area, volume, again, is area times the height. Well, the area is staying the same. It's the cross-sectional area of the tank that remains constant. What is changing is the height. So we have the change in the height over the change in time. And so that's going to equal the negative flow rate, which is the negative cross-sectional area of the hole times the velocity at position 2. So if we simplify this, we get the change in height of the fluid over a change in time is equal to the negative cross-sectional area of the hole times the velocity at position 2 divided by the cross-sectional area of the tank. So this equation that we derived here, we can actually code out using, obviously, plugging this equation in for velocity 2 to create this model using a code. Real quick, before we begin coding though, we need to correct one small mistake within this derived equation, and that's over here in the velocity at position 2, and that is that the height of the initial fluid height should be in the numerator and the height of the fluid should be in the denominator. And so that brings us all the way back over here. And so the mistake was made when we were defining our volume and a number of moles. So the number of moles, although it's changing, we are dealing with the height of the initial fluid, whereas with the volume is also changing, and that is dealing with the actual height of the fluid. Because, so with moles, the volume is based off of the initial position, whereas the volume is constantly changing, so that's why it's not the initial height there. So now we can begin writing out this code to ultimately create the model of the fluid height over time. So to do that, we're going to be working in something called Collaboratory, which is essentially Python. And so what we want to do is first import some paths that will allow us to solve for this system of ordinary differential equations. So the first thing we're going to import is numpy. This is a mathematical pack that just allows us to perform mathematical functions like square root, which is what we need in our velocity at position 2 equation. We're also going to import from scipy dot integrate. We're going to import solve IVP. So solve IVP is a function that allows us to basically input a function with an independent variable, which would be the time, and it will use that and will use the output of the function that we defined, which is the dependent variable, as a vector to solve for the solution that we're looking for. It solves the system of ordinary differential equations. And then also, because we want to create a model and graph it, we're going to import from plotly.subplots. We're going to import make underscore subplots. So those are the packs that we're going to be using. And so the first thing is, when we're using solve IVP, we're going to need to have a function. So we need to define the function. So what function we're going to define is the right-hand side of this differential equation here. And so we're going to have the independent variable, which is time, and the dependent variable, which would be the vector. So we'll just call the vector y, but now we need to unpack what that y is. Well, that y is ultimately the height, and because it's a vector, we just want the first part of it, which in our case there's only one, but if we were solving something with multiple arrays, we would want the first indice of it, but because we only have one, it's not a super significant, but we do need to unpack it, and so that's going to be the first index, which is actually 0 instead of 1, because that's what the Python syntax is, and that's going to be our height. And then what we need is what we want it to return to us when we define the function. So we want it to return, this negative cross-sectional area of the hole times the velocity at position 2 divided by the cross-sectional area of the tank, because that's the right-hand side of the equation. And so again, with vectors, everything has to be in brackets. So cross-sectional area of the hole times the velocity position 2 divided by the cross-sectional area of the tank. And so cross-sectional area of the hole and cross-sectional area of the tank is something we're both given, but the velocity position 2 is an equation that we derived, so that's going to be the square root So we have a square root of 2 times the quantity of the gravitational acceleration times the height plus the 101,325. That's actually just the pressure outside, so we'll define it right now as pressure external, and then we'll go back and define that as the constant of 101,325 divided by the density, which is rho, times the quantity of the height minus the initial height divided by the height of the tank minus the height of the fluid, and that's going to be minus 1, so that is all going to be in parentheses. So let's see, one more. Okay. So now we have all of these variables that we need to define. So first we have gravitational acceleration. That's going to be 9.81 meters per second squared. And then we have the pressure external. So that's going to be 101,325. That's pascals. And then we have the density, which is 1 times 10 to the third, and that's kilogram per meters cubed. And then we have the height of the tank, which we are given is 1 meter. Then we have the initial fluid height, which we are also given as 0.9 meters. And then the cross-sectional area of the hole we are given is 0.001 meters squared. And the cross-sectional area of the tank we are given is 1 meter squared. So now we have all of our terms defined, and we can enter all of that in. So now we can use our solve IVP. So first we need to give it a function that's going to be our right-hand side. We also need to give it the independent variable, or the time span. And so that's going to be 0 to whatever finish time we would want. And then we have to give it the initial value, so that's going to be hi. And then the method that we're going to solve with, we're going to use the Radu method. And then dense output true, this is just going to allow us to solve it if it were true. And so it's letting us know that we didn't determine an end time, so we'll just put it up here with the other defined variables so that we can change it to whatever time we would want. So we'll start with 4 seconds, or let's start with 10 seconds. And so we'll give this a name, so we'll call it resolution, shift enter. And so it is telling us that our array must not contain infinities. And so basically what's happening is eventually when you are draining a tank, there will be no more fluid in the tank, and the height of the tank minus the fluid tank will essentially become a negative, which the computer can't really process that right now because we haven't told it that. And so it's just solving until the end of seconds. But because of that, eventually it's becoming negative, and when you have a negative in a square root, that's not going to be okay. So what we can do is, one, we can shorten the time. So if we were to shorten it to 4 seconds like earlier, everything would be okay, and we would be given the resolution. But what happens is that's not when it completely reaches steady state, because we don't know at what point it reaches its steady state, at what point it reaches 0. And so because the issue is the negative, maybe if we were to put an absolute value in this equation here, and we were to change this back to 10 seconds, everything looks okay. So let's go ahead and try and plot this. So we're going to make the x values. So the x values, we'll just call tplot, is going to be linearly spaced values. So we'll use np lin space. This is going to create us values from a start value. So we'll start at 0. We'll go to, let's just go to t-end, and we'll have 500 values in between. So that's going to be our plot, and so we're going to make a subplot, so we'll call it figure equals make underscore subplots. And so we need to add to this, so we'll add fig.add underscore scatter. So our x values is going to be our t-plot, and our y values is going to be our resolutions. And we'll just, because it's an array, we want the first value of the resolution, and we want it of the solutions. So if we just put 0, it will make our subplots. should make our subplot to make it of the solutions of the solve by VP. So it's not actually going to be in parentheses, it's going to be dot sol, and it's going to be of the x values, which is the t plot values we defined earlier, and of course the first index of it. And so that makes a model, but because we put that absolute value in it, what happens is the fluid is decreasing with time. It reaches 0, and then it kind of continues to go, even though there's no more fluid to escape, but because we put in the absolute value, computer doesn't really recognize that. It just keeps going, and so that's why we have that kind of influx back of the graph, and it kind of creates a small wave. So how do we combat that? Well, Solve IVP actually has something called events. Basically, whenever we give it a function, whenever that function equals 0, that's the event, we can actually terminate it, and so it will stop. And so what we are looking for is for this event to equal 0. Well, what's that event we're looking for? That's when the velocity at position 2 equals 0, because once it equals 0, it's going to become negative, and we want it to stop before it becomes negative. And so what we can actually do is define another function, and this can be when the velocity of 2 is at its event. Velocity of 2 goes to 0, that's our event. And again, we need to give it the same things as when we defined the function earlier, so we'll need the time and the vector coming out. And so that's going to be, again, we have to unpack the vector, so that's going to be the height of the first index of the vector, or the height equals the first index of the vector. And then so we needed to just return that equation, and so it's this velocity 2 equation here. So we just need what is inside, because we don't need the square root and we don't need the absolute value, because we're just looking for when that equals 0. And so now that we have that, we want to tell it to terminate once it equals 0, and so we actually have something called v2 0 event. So whatever your function is, dot terminal, and when we say that that is true, basically what that means is once it reaches 0, it's going to terminate. And so now we can add this into our resolution here. So we can say events equals v2 0 event, and we'll want it to be of, or it'll be in brackets because everything's in an array, so you always want brackets. Shift enter. And so if we shift enter again, we can actually see we have the t events, and this 4.56 is actually just like the number of seconds that it takes to reach a 0. So anything past that, that's why when we were doing 10, like anything past that is empty, so it didn't really work very well. And so now that we have that, all we have to do is change the amount that it goes to. So it's not going to go to t end or whenever the time stops. We have set up defined in all the variables. It's just going to go to whenever the t events, whatever that solution is. So we're going to use the res, which is the solve by VP dot t underscore event, and so we're going to do that of t plot, which is, we're just going to get that first index. And because it's an array, we have to get the first value of the first index. So we're going to have 2 brackets with 0 inside. So if we shift enter, we now have that model of the height of the fluid over time. And so using the equations that we derived and SciPy that integrate with its solve MVP and it event terminates, we are able to create this final model demonstrating the fluid height over a change in time.